Hello everybody and welcome back. So in the last video we solved problem 7 of the 2020 AIME I in two different ways. The first way was using some messy casework and the second way was with Vandermonde's identity. If you haven't watched that video, there should be a link in the top right corner. But I didn't actually prove this theorem in that video. So this is what we're going to do today. We have the identity right here. M plus n choose k is equal to the summation from r equals 0 to k of m choose r times n choose k minus r. So we're first going to consider the binomial expansion of 1 plus x to the m plus n. And whenever we're dealing with binomial expansions, we'll want to use the binomial theorem. And using that, we find that this is equal to m plus n, and then over here we have k equals 0 of m plus n choose k times x to the k. Alright, this is one way of writing 1 plus x to the m plus n. But we can also write 1 plus x to the m plus n as 1 plus x times to the m times 1 plus x to the n. And over here I just split this exponent over here into two different parts. Alright, so now what we're going to do is we're going to basically write this, use what we found over here to simplify this. So instead of m plus n, we'd have m, and then same for here we would have n. So this first part would be summation of m, and the bottom is still k equals 0 of m plus, it would be m choose k times x to the k. And then for the 1 plus x to the n, we would have the summation of n k equals 0 times n choose k times x to the k. Now we can just write these summations out. So the summation from k equals 0 to m of m choose k times x to the k. So k is initially 0, so we would have m choose 0 times x to the 0, which is just 1, and then plus m choose 1 times x, and then plus m choose 2 times x squared, and so on. And then we would multiply this by this summation. So we would do the same thing. So we would have n choose 0 plus n choose 1 times x plus n choose 2 times x squared, and so on. Alright, so now we can just expand this product out. So we would have m choose 0 times n choose 0 times x to the 0, which is just 1, but you'll see why I included that in just a second. And then for the x to the 1 coefficient, we would have m choose 1 times actually would be m choose 0 times n choose 1 plus m choose 1 times n choose 0. And that is the coefficient for our x to the 1 term. And then finally, this coefficient would be really long, so hopefully I can fit it in here. So we would have, let's see, m choose 0 times n choose 2 plus m choose 1 times n choose 1 plus n choose 2 times n choose 0, and that's all time multiplied by x squared. And this goes forever. So we would keep doing that same. We would just keep foiling this product, which is essentially what I just did over here. And you can see pretty clearly from this that the coefficient of x to the k would be m choose m choose 0 times n choose k, and then plus m choose 1 times n choose k minus 1, plus, this keeps going, and then this would go up to m choose k times n choose k minus k, which is just 0. And this should remind you or look familiar to you because of the binomial theorem. It looks very similar to the binomial theorem. Not exact, but very similar. So how can we use this? Well, we can go back to what we found over here. We found that the coefficient of x to the k is the summation of from k equals 0 to m plus n of m plus n choose k. That was the coefficient of x to the k. And over here, this would also be, this is also the coefficient of x to the k. Therefore, we can set these equal, and this is where the magic happens. So we can set these equal, and also we can note that this is, we can write this as a summation, so it's more concise. This is equal to from r equals 0 to k of n choose r times n choose k minus r. Alright, so this is the coefficient of x to the k, and n plus n choose k is the coefficient of x to the k, so they must be equal. So we can set these equal, so we would have n plus n choose k, and that's equal to the coefficient, the quantity we got here, which is equal to k r equals 0 times n plus m choose r times n choose k minus r. Alright, actually let me just move that to that. Alright, and look at this. This is the Vandermonde identity. So basically we used the binomial theorem to find the coefficients of x to the k, and we also wrote 1 plus x to the m plus n as a different form, and we worked with that, and we found both we found the coefficient of x to the k in two different ways and set those equal, which led us to the Vandermonde's identity. This, my friends, is one of the most elegant algebraic proofs you will ever find. Now there's also a combinatorial proof, which I'll not cover in this video, but you can find a good written proof of using the combinatorial way in the description down below. Alright, hope you guys enjoyed. If you did, be sure to leave a like, subscribe, and comment down any other videos you want me to do. I'll catch you in the next one.